Good day. I am Eric M. Inocencio and I will be presenting to you my research entitled Response Evaluation of Locally Deployed Neutron Survey Meters in Different Neutron Fields, under the supervision of Dr. Roland Caballar and Dr. Albi Astronomo. The discussion will be covering several parts. It will include a short introduction, objectives, methods, preliminary results, preliminary conclusions, implications, further activities, Gantt chart, and some references. Linear accelerators play an important role in radiotherapy by delivering radiation doses to patients with minimal calculated risks. Lower skin dose, higher dose in depth, reduced scattered dose to healthy tissues, and less rounded isodose curves are some of the advantages of high-energy photons in LINAC. However, this modality has a drawback. When LINAC operates above 8 megaelectronvolts, neutrons are produced. In the process, accelerated electrons or high-energy photons interact with the heavy materials in the accelerator head, resulting in neutron production. Also, in medical cyclotrons, which produce isotopes for nuclear medicine, neutrons are generated as a byproduct when accelerated particles hit the target in the process. Neutrons have different distributions at different locations in a given facility. The neutron spectrum shows the relative distribution of thermal, epithermal, and fast neutrons at specified locations. As an example, Montanil's study selected three locations in a LINAC facility for neutron spectrum evaluation. At the location nearest to the source, the neutron spectrum shows that fast neutrons are dominant, while at locations far from the source, thermal neutrons are dominant. Because patients lie near the source, the neutron dose contribution would be significantly coming from the fast neutrons. This data is an example of the neutron dose measured at different locations in a linear accelerator facility. To evaluate neutron dose, it should be emphasized that dose conversion coefficients are highly dependent on the spectra, that is evident in this plot. This indicates why survey meters are limited in measuring neutron dose in a facility with different neutron distributions. The goal of the study is to investigate how the neutron distribution or the neutron field is easily affected by introducing a small volume of a material. The research goals are to calibrate locally deployed neutron survey meters in a CF252 reference field, to investigate the effect of different materials on the neutron spectra at a specified irradiation location, to compare the response of different neutron survey meters with a modified Bonner-Sears spectrometer in different neutron fields, and to derive correction factors for the neutron survey meters for characteristic neutron fields.
This slide shows you the flowchart describing the calibration procedure, shadow cone method, recommended by the International Organization for Standardization or ISO. First is to get the total field count CT. Second is to get the scattered field count with shadow cone CS. Third is to get the difference of CT and CS to get the direct field count or CD. Fourth is to convert this direct field count to count rate by dividing the direct field count by the exposure time. Convert fluence rate to ambient dose by dividing the CR or the count rate by the factor of ambient dose equivalent to be found in the certificate of the instrument multiplied by the air attenuation coefficient. To get the personal dose, we multiply the fluence rate by a constant from SRS 16, which is 400 for Californium 252, and the unit is picosievert per cm squared, where our fluence rate would be the direct count rate divided by the factor from the certificate of the instrument multiplied by the air attenuation factor or coefficient. Finally, get the relative response R by dividing the dose measured by the instrument over the dose from the reference meter. which is, in this study, is from the LC nuclear. To get the calibration factor, we just get the reciprocal of the response. This calibration factor will be multiplied to the doses measured by the instrument to get the correct doses.
The calibration setup follows an ISO cube, which is 3 by 3 meters in dimension. The standard distance of the source in the detector from the walls and the floor is 1.5 meter, while the source to the detector distance is maintained at 1 meter. To place the shadow cone, the distance of the source and the end of the cone should be at least twice the height of the source, which in this case is 3.8 centimeters. The left figure shows the calibration setup without the shadow cone for total field measurement, and the right shows the setup with the shadow cone for scattered field measurement. These are some pictures showing how the calibration setup is configured in the BNRI SSDL Neutron lab. The left side shows pictures for total field measurement, and the right side shows pictures for scattered field measurement. The upper left picture shows the dineutron setup. The lower left shows the radii setup, and the lower right shows the ELSA nuclear setup. So far, we have three survey meters on study. The first one is the neutron survey meter from ELSA Nuclear, Italy, with an HE3 proportional counter detector with an HDPE 10-inch spherical moderator, giving us counts as data. The second one is the Dineutron from Canberra, USA, with two HE3 detectors with dual sphere moderator, with diameters 2.5 inches and 4.2 inches. It has a dimension of 260 by 367 by 140 millimeters, and the selected unit for experimental data is millisievert per hour. The last one is the Rad-Eye Neutron Pager from Thermoscientific USA with a cesium-doped CLYC scintillating crystal detector. Its modifier could be a tissue-equivalent material like a water phantom, according to its manual, with dimensions 96 by 61 by 31 millimeters. The selected unit is microsievert per hour.
The field modification setup follows the ISO cube 3 by 3 meters with 1 meter source detector distance and 1.5 meter distance from the walls and the floor. The modifier is placed 20 centimeters away from the source. The picture on the left side shows you how the setup is done. To demonstrate how the neutron field can change with modifiers, these modifiers are placed 20 cm away from the source for optimum effect. Then, measurement with neutron survey meters were done 100 cm away from the source. Finally, results from the neutron survey meters obtained in different fields were then compared. These are the pictures showing how the modifiers are placed on the aluminum bench 20 centimeters away from the source. The modifier stand used is a combination of the 1.1 meter high steel frame with aluminum plate, where the 0.3 meter high aluminum bench is placed. Effects of the aluminum bench is not accounted because these materials do not significantly interact to neutron fields, therefore with negligible effect on the neutron field modification. The upper row shows the setup for concrete, lead, and aluminum, while the lower row shows the setup for water phantom, polyethylene, and graphite modifiers from left to right.
Here is the field modifier profile showing their corresponding dimension, density, and composition. The thinnest is the aluminum modifier and the thickest is the concrete modifier, which dimensions are based from the NCRP recommendation for concrete walls and a radiation facility. The shortest modifier is lead and the tallest is polyethylene, which is a common material for moderating neutrons with compositions of large neutron cross-sections, which means more likelihood of neutron interaction. Table 1 shows the relative responses and calibration factors of radii and dineutron with the reference meter LC nuclear. For radii, the relative response is 0.4573 with a calibration factor of 2.1865. For dineutron, the relative response is 0.4356 with a calibration factor of 2.2956.
Table 2 shows the summary of the dose rates of modified fields in microsievert per hour per survey meter. Figure 1 shows the unified graph of dose rates in microsieverts per hour per modifier per survey meter. Relatively, those measured using RAD-I has the highest doses and those with LC-nuclear has the smallest doses. Field modification in water phantom using RAD-I is not available yet since the researcher lacked one more phantom to execute the procedure. Remarkably, the pattern is similar for the three survey meters, with alternating dose rate peaks at lead or aluminum data points and lowest with water phantom. Here are some preliminary conclusions in the study. The response ratios obtained for the dineutron and radii neutron survey meters are 0.4356 and 0.4573 respectively, while the corresponding calibration factors are 2.2956 and 2.1865 respectively. The calibration factor should correct the doses measured by the instruments. However, results show that corrected doses differ even after applying the obtained calibration factors. The differences were also found to vary depending on the field modifier that is used.
The following are listed as some of the study's implications. The inconsistent results indicate that the calibration factors derived in reference fields will be insufficient to correct the neutron survey meter dose estimates when used in the workplace. The remaining part of the study will therefore focus on the derivation of more appropriate correction factors for the neutron survey meters for different characteristic neutron fields. The result of this study can be applied by the neutron survey meter users to facilitate more accurate neutron monitoring for radiation protection purposes. The Gantt chart shows the timeline of the researcher and completion of this research. The researcher is looking for a locally deployed neutron survey meter since the one confirmed in K-Health was found out to be defective. Also, the researcher is in search of an extra water phantom for the completion of the RAD-I field modification data. Currently, measurements are gathered using the Bonner sphere spectrometer of PNRI, named HEMUNS or the helium-3 multisphere neutron spectrometer, to be used as a reference of comparison for the modified fields using the other survey meters. Here are some of the important references used as the basis of this research. Your valuable suggestions and expert recommendations for this study are welcome. Thank you for listening.